As anyone who's ever done oscillator design will tell you, it can often be a very time-consuming trial and error process, both in selecting the correct topology for your particular application, as well as fine-tuning and tweaking a topology once you've selected one. So this is where it's really nice to be able to simulate your designs in software before you go to the bench and start building them. Now I need to build a 19.2 megahertz oscillator, and I of course have some 19.2 megahertz crystals, and I'd like to use them in a Pierce gate oscillator configuration. But before I commit to this topology, I really want to evaluate A, whether I'm going to have sufficient gain margin for this oscillator to start up reliably, and B, to make sure that I'm providing a good loaded Q for the crystal, because crystals have very high Qs, but when you stick them in the circuit's going to degrade their Q. So you really want to make sure that you keep that loaded Q when the crystal is inserted into the circuit high in order to maximize stability. And to do that, I'm going to be using Genesys, which is not really a piece of software that's within the typical hobbyist budget, but I've got a 30-day trial to it, so I thought I'd kick the tires and see what it can do. So I'm going to synthesize a new oscillator design, and we'll take the factory defaults, sure. And I'm going to pick a crystal Pierce oscillator here and stick in the frequency that I want to run it at, 19.2 megahertz. And when I do that, you'll notice it fills in some of these motional parameters for the crystal. Now, if you know the motional parameters for your crystal, you can put these in manually. I have not measured the motional parameters on this crystal at all, so I'm just going to take the defaults here and hit apply. So you can see it's already generated a couple things for us. It has a basic Pierce oscillator schematic here. There's also a open loop match here, because this does do open loop analysis. We've opened the feedback loop here, and we have a port 1 and port 2. Which normally would be connected in the circuit, but obviously it's been opened here for analysis purposes. And it's also plotting the gain and phase shift over frequency up here in this top graph, which is quite nice. But I want to take a look at the schematic here real quick. As I mentioned, we have an open loop analysis going on here, so we've opened the loop and we have a port 2 and a port 1. If you're only doing linear open loop analysis, you don't really need port 3 here, but if you want to do like transient analysis and stuff, port 3 is used for that. Now, this is a pretty typical single transistor Pierce oscillator, but that's not really what I want. I want a Pierce gate oscillator, so I'm going to pretty much delete this whole schematic here and put in my own. So I've duplicated my circuit here in Genesys, and I'm just using a pair of NMOS, PMOS transistors here to simulate the inverting gate. I've also put another pair here as an output buffer. But this is the main pair here that's going to actually be doing the oscillation. We have a 1 mega ohm resistor here tied between the input and output to bias this gate into a linear state. We have the typical feedback network here with the crystal in it for a Pierce oscillator. And there is a series resistor which I've added here. You don't have to have this resistor here, but it does help to isolate this capacitance from the output of the gate. And it also helps to reduce the current and hence the drive through the crystal so that you're not potentially overdriving the crystal during operation. So let's see how this thing works. We can run the analysis here and take a look at what we get in our graph. And again, we get a plot of gain and phase over frequency here. And you can see that the phase slope here crosses the 0 mark way down here, which is not at all what we want, because the oscillator, of course, is going to oscillate when the total phase shift through the loop is 0. And if we have a gain of 1 at that 0 phase crossing, then we should oscillate. Now, obviously, we don't have a gain of 1 there. Our gain is going to be, according to this, something like negative 19 dB. So obviously a gain of 1 would be 0 dB. So we'd want something greater than 0 dB. So a negative gain here is certainly no good. So according to this analysis, this circuit should not oscillate. But there's only one little problem with that. I have the circuit built up here on the bench, and as you can see, it's oscillating just fine. Now, of course, this isn't a problem with Genesys. It's a problem inherent to performing an open loop analysis. So what's going on here is the system is injecting a signal, and it's really sweeping a range of frequencies here, into port 1. And then it's measuring how much of that energy comes out on port 2. And that's where we're getting this nice little phase shift and gain graph here. And you can see, if we look at the graph properties, that these are being calculated entirely off of the S21 parameters. In other words, how much power is transferred to port 2 from port 1. The problem with that is, when we actually build this oscillator on the bench, we don't have it open loop, we have it closed loop system. And so we have to close this loop in order for the system to oscillate. And so if we don't have our port 1 and port 2 here well matched to the rest of the circuit, then it's not going to accurately represent the impedance that's going to be seen by the circuit when it's actually closed. And we can actually see that very clearly over here in this plot of the S22 and S21 parameters. So we see the output reflection, the reflected power from port 2 here in red, and you can really just barely see S11, which is the input reflection, the power reflected from port 1. So if we go into graph properties here, we can make this a rectangular graph. I think that'll show up a little better here. So we can see that the reflected power from the output port, S22, is not terrible. It's negative 23 dB. And we want this to be lower, obviously, because we want less reflected power and more power transferred forward. However, if we look at the reflected power here on the input, it's really bad. It's like, what, negative 0.004 dB. So we have a really poor match here in our open loop analysis, and that tells us that this gain and phase shift graph are not going to accurately represent what actually happens in the circuit when we close the loop. Now, we could try to improve the port matching in our simulation, but that's often inconvenient. Luckily, there are a couple of really smart guys named Terry Hoke and Mitch Randall who came up with the aptly named Randall-Hoke equation. And I'll put links to some of the more technical papers on the subject in the video description. But the TLDR is that this equation represents the actual open loop gain of our circuit, regardless of open loop termination mismatches. And we can also see here from this equation that if S12 is small and the product of S11 and S22 are small, then this equation will be approximately equal to S21. However, if those conditions are not met, then there can be significant error between the actual gain through our circuit in open loop configuration versus just using the S21 parameter, which we've been using so far for representing our gain and phase angle over frequency. So I've added the Randall-Hoke equation here into Genesys, and I've also put in some convenience variables here for calculating the gain, phase angle, and loaded Q based off of the Randall-Hoke equation. So if we go into our open loop gain graph here, we can replace these gain and phase markers that are based off of S21 with our new data. And now that we've done that, we can see very clearly that at the 0 phase crossing, right here, our gain is positive 5 dB. And I've also added a plot of the loaded Q, and you can see that the Q peaks right here at the 0 phase crossing, which is excellent. Now this Q is divided by 1,000, so this is actually 21,000 instead of just 21. Otherwise it would be way off the chart here. But this is actually quite good. If you look at the motional parameters of the crystal that we're using here, this crystal has an unloaded Q of only about a little over 24,000. So this is an excellent loaded Q of just under 90%. So that's really very good, and that's due primarily to the high input impedance of the CMOS gate. Now, while the high loaded Q will give us good short-term stability, we also are concerned with medium-term stability, in particular stability over temperature. Now, I do expect this particular oscillator to have pretty good temperature characteristics because the crystal itself is rated at 10 parts per million stability over temperature. But one of the things you have to look out for is internal heating of the crystal. So if you're driving too much power and dissipating too much power in the crystal, that can cause self-heating, and this shows up particularly at startup. So the crystal will start warming up as soon as you turn it on, and that can cause excessive frequency drift. So I've got it in my little oven here, and we're going to let it acclimate at 25 degrees Celsius. And with it held at that steady 25 degrees Celsius, we'll see how much frequency drift we get over the first 10 minutes of operation. All right, well, there you have it. That's a full 10 minutes. And this thing drifted about 1.5 hertz in the first minute, and a grand total of 0.2 of a hertz over the next couple of minutes there, and it's just been rock solid here after the first 2 or 3 minutes. So definitely very good stability out of this, and very little drift at power on, which means we have very little power dissipation in the crystal, which is excellent. And I did also test it over a wider temperature range as well, from 20 degrees Celsius up to 70 degrees Celsius. And I had no trouble getting the oscillators started over that entire frequency range. And as you can see, the maximum deviation from the nominal frequency here at room temperature was less than 4 parts per million over that entire temperature range. And this is really quite good performance, especially considering that there is no temperature compensation in the circuit at all. So I'd like to give a special thanks to Randy Ray for very patiently fielding my questions as I fumbled around with my Genesys simulations. If you haven't heard of him, he literally wrote the book on oscillator design and simulation. Twice, actually. So if you enjoyed this video, which I hope you did, I highly recommend you pick up one of his excellent books on the subject. And as always, if you have any questions, suggestions, or corrections, please leave them in the comment section below. Thanks for watching.